CMake is an open-source, cross-platform development tool that's used to generate build system configurations. You don't need to fully understand specific build systems like Ninja or Make. Instead, CMake handles all the configuration and building for you. ESP-IDF relies on CMake to help build projects as well as include necessary software components and libraries. I'll give you a brief primer on how to use CMake without ESP-IDF so you can get familiar with the syntax before showing how it's used to build ESP-IDF projects. Understanding CMake is useful for configuring larger embedded applications, as many frameworks like ESP-IDF and Zephyr rely heavily on it. Before we start, I want to let you know about my ESP32 IoT course. If you're enjoying this content, I highly recommend checking it out. We start with the basics of ESP-IDF for writing professional code for the ESP32, then learn how to read from connected sensors and transmit that data over Wi-Fi using HTTP REST API calls to an IoT platform. We'll also tackle publish-subscribe mechanisms with MQTT before seeing how to secure everything using Transport Layer Security, or TLS. By the end of the course, you'll have the chance to build a full IoT sensor that publishes data to an MQTT broker, and you'll earn a digital certificate to showcase your new skills. Click on the link in the description to sign up. Let's start with a basic CMake primer. We won't use ESP-IDF for this. In fact, we're just going to rely on our basic build systems to make this happen. Let's minimize any apps you might have open, and we're going to create a new folder. We're going to call it CMake_demo. We're going to create a very simple Hello World C program, but we're going to do so by creating a library. The first thing we'll do is create this include folder, and let's create mylib.h. In our library, we're just going to declare a very simple function called sayHello, and we will create some header guards around it. So if not defined, mylib.h, let's go ahead and define that. And I made this mistake here. We will define that symbol so this header file can't be included more than once. We will declare our function sayHello and end that macro. Let's save that. Then we're going to create another folder. We're going to call this src for source. And it looks like it's trying to include it under include. So we're going to drag this to the directory one above. Now we have our CMake demo directory, include and source as separate directories. In source, we want to create mylib.c. We'll first include the standard input output, which is useful for things like printf, and we will then include the mylib header file. Don't worry about giving it a relative path to that include file we made, because we're going to have CMake find that for us. So normally you might do something like, go up one directory, include, and then define it from there. But we're just going to say mylib.h because CMake is essentially going to glob all of the files it finds when we point it to this include folder, and our source code will know where to find it as part of that CMake list of header files. Then we're going to define our very simple function. We'll call it sayHello. It doesn't return anything, so return void. In that, we will just print f, hello world, new line, and that's it. Let's save this. And we're going to create main.c as our main application. Let's get rid of my search bar here. We will include mylib.h in our main. This is our main entry point. We will call our sayHello function. And like any good OS program, we need to return a value. In this case, 0 says nothing went wrong with the program. So we will save that. To use CMake, we need to create a CMakeLists.txt file. In this case, we're going to make it at the top level of our directory. So new file, CMakeLists.txt. Notice the Camel or Pascal case here. The spelling is very important because CMake will look for exactly this file when we run CMake. The first thing you will often see in most CMake lists files is this CMake minimum required. This is the minimum version that CMake should use when building this project because it determines which functions are expected to be found within these CMakeLists.txt files within this folder and any subsequent recursive folders it might come across. We're going to specify version 3.16 because that's what we've been using in ESP-IDF. We're going to give this project a name. We'll call it Hello World. We'll give the project a version, in this case 1.0. We'll give it a description, call it the classic, and we'll give CMake some hints about what languages it can expect to find within this project. In this case, it's just going to find C. Next, we're going to create a static library target. We're going to call it mylib. A target is an output of the build process. This is any output. This could be a module, this could be a component, or a library. It could also be things like an executable or an interface. There are others, but for our purposes, we're going to be creating a static library. We're going to denote this library as static, which means it should be built into the final program rather than a dynamic library, which is loaded in at runtime. We will then tell CMake where to find the source code for this target. In this case, it's going to find it in source mylib.c. Then we want to set the include directories for the library so that our source code, both main and mylib.c, know where to find that mylib.h header file. We will specify the target, which is mylib. It should match the argument we set in that add library function earlier. And we will specify public, which adds the directory to the search path for any targets that might link to this target or this library. CMake current source dir is a variable known within the CMake system. It's the path to the directory that's currently being processed. So this directory, in other words, which would be CMake demo. Within that, it should look for this include folder, which we have right here, and look for any files within that to create that list of includes or header files that the source code can then include. This is that function that allows us to go into mylib.c or main.c and just say mylib.h, and it's not worried about the exact path to find those. This function allows that to happen. Then we're going to call this add executable. This creates a target similar to the add library target, but instead of the target being a library, it's going to be an executable. We're going to use the same name as the project name by using this project name variable that's within CMake once we called that project function earlier. So now the executable will be called Hello World, and that's the name of that target. We will provide the source code for that, which is source main.c. Finally, we link the library to the executable. We can either make this a private linking, which means that the library is not exposed to any targets that then depend on this target. And remember that the target here might be another library, right? You could have multiple chains of libraries. So private says don't expose, in this case, mylib above that. But in our case, this is an executable, so it doesn't really matter if it's private or public. But for good practice, we will keep it as private. And this is where we link mylib. We call it out specifically as the third argument here, and it links to the executable target given by project name. I'm going to add another line here just for good coding style and save. Let's bring up a terminal. We will make sure we're in workspace. Notice that it will enable ESP-IDF by default, even though we are not going to be using ESP-IDF. If you're using the Docker file that's recommended as part of the repository linked to in the description, you will have access to things like GCC, Make, as well as Ninja for potentially building C and C++ applications. We also obviously have CMake, as that comes with ESP-IDF. In fact, if we call CMake, you can see our options here. When you come across instructions to build applications using CMake, you will probably find a flow that looks something like this. You will first make your build directory, although I am not in the correct space to do so. So let's remove that. Let's go into apps, and then let's go into our CMake demo. Great, here's our source code. Now we want to make our build directory. So we have that within our project. You then go into the build directory, you call CMake and then give it a context. In other words, where can CMake find that top level CMakeLists.txt file? And that's going to be one folder up. So CMake is going to run and it's going to generate some files in that build directory. So if we go to our CMake demo, you might have to refresh files if you're in VS Code. You will see this build directory and it generates some files for us. By default, CMake is a meta tool that relies on a number of underlying build systems. In this case, it is defaulting to Make. Hence, it creates this Make file. And you can look through this, and it's just a Make file if you've ever worked with Make before, but it might be a little difficult to read because it is automatically generated by CMake. So it has all these funky variables and names in here that might be a little tricky to figure out what's going on. Back in our terminal, because we have that Make file, we can just call Make, and it builds our application. Now we should have a file in here called Hello World, and that is our executable. So if we run this, it just prints to the console, Hello World. Let's go up a directory, and let's remove that build directory. And this is a normal CMake flow. Once you're done building something, you can copy out your executable or install it, and now you can remove that build directory, and it cleans up any of those artifacts that might be built in the process. Ever since CMake version 3.13, we can specify the build directory. We don't need to go into it like we used to have to do, like I just showed you. So we can call CMake-S, notice the capital S here. This is the path to the source folder. In other words, the context, where can it find that top level CMakeLists.txt, which is the current directory of our project. Then we give it -B, and we tell it the name of the folder we want it to build within this context. So we're going to call that, and you'll notice that once again, it creates this build directory with similar files. We still don't need to go into build to see what's going on or to build the project. And we don't have to call Make manually. We can just call CMake-build, which says to use whichever build system we generated our files for. In this case, it is Make. It defaults to Make, so it created that Make file, and we will specify the build folder. It will know to call Make, it calls Make, and builds our target. Now we can say /build, go into the build folder, and call our executable. Once again, it prints Hello World to the console. Let's go ahead and remove that build folder again. If we type CMake-H for help, you can see a list of generators that are available on this platform. Most of the time, it defaults to Unix Make files, hence why we've been calling Make. But we also have Ninja installed thanks to ESP-IDF. And we can specify which generator or which build system we want to use when we call CMake. So now we can do CMake-S period for the current directory as context. We want to give it the name of our build folder, so build, and -G for the generator. And notice the quotes here for the string. We're going to call Ninja, so it should line up with this string here. Press enter. It's going to now generate build files that Ninja can use instead of Make. So let's refresh our documents. Up here in VS Code, you can see instead of the Make file, we have build.ninja. And this is Ninja's version of a Make file. It describes the instructions to build the project. So let's close that. We can come back to our command line. And we don't even need to know how to use Ninja. We can just call CMake-build, give it the build directory. Oops, it looks like I need to call CMake-build and give it the build directory. Now it should call Ninja on the back end, and that will build our project. So we can once again go into build, give it our executable name, and it runs just like we had built it with Make. Let's go ahead and remove that build directory. CMake is a very complex and deep tool. I recommend diving into it if you want to make larger and more complex projects. I also recommend this free ebook, An Introduction to Modern CMake. The author does an amazing job of walking you through the various components of CMake and giving you great examples and demos to work from. If you navigate the ESP-IDF documentation, you can find a build system section under API guides that goes into a lot of detail about how the build system actually works. In here, there is a recommended directory structure template and a minimal required CMake lists file. At your project level, you just need these 3 lines. Specify a minimum CMake version, import the ESP-IDF specific CMake functions, and declare the project with a name. By default, the build process will look for a directory named main in your project folder. It will automatically include source code found in that directory. Let's go back and look at our Blinky example that we made in a previous video. If we look at this seemingly simple CMakeLists.txt, hopefully we have a better understanding of what's going on. The CMake minimum required function sets the minimum required version for CMake to build this project because of the various functions it might find within. You will almost always see this called at the top of just about every project level CMakeLists.txt. We then set up the ESP-IDF build environment. This include function works similar to the include macros you might find in C or C++, where it just copies in all of the code found in this project.cmake. If we go into Tools, CMake, project.cmake, you can see where ESP-IDF includes other CMake files. So this gets pretty deep in all of the customization of CMake that it's doing, but it's also doing things like defining custom functions that can be used. In other words, it's extending what CMake can do by providing these functions so you can actually use these in your CMake files to do things like define an ESP-IDF specific component or library, and that has a certain meaning within the context of ESP-IDF. So you are welcome to look through these and see all of the functions that ESP-IDF defines, but know that it essentially makes a lot of the defining components, defining libraries, and linking everything much easier for us. So we can get out of that and go back to our CMake lists. And then all we need to do is define our project name. This sets the name for the executable target. In this case, it's app. So when we build the project, it will build everything and link everything to this target, this app target, and name the output executable, whatever you put in here. So in this case, app. So app.bin is the binary file that is the output of the build process from within ESP-IDF. In the command line, I'm going to go out of CMake demo, and I'm going to go back into Blinky. When you call idf.py -build, that sets a couple of parameters and calls CMake to both configure and build our project. It's just a wrapper tool for us. When we wrote this Blinky demo and called the set target function, it created this SDK config file for us, where it defines this IDF target symbol and gives the variant. In this case, it's the basic ESP32 variant. It can be helpful to redefine the target here every time you want to build for a new target. You can also define it in an SDK config or set up some defaults, which will be covered in a later video. For now, the easiest thing to do to see how to work with CMake without using idf.py is to get rid of these generated SDK config files. So I'm just going to delete them and know that we won't have any conflicts. I'm also going to remove the build folder, refresh my files, and you can see I'm set up with the basic code that we wrote in a previous episode. Remember that IDF target symbol we saw? That is a custom symbol that the CMake extensions for ESP-IDF look for when it's trying to figure out which target to build the code or application for. So instead of setting it using something like the idf.py set target or within that SDK config file, we can actually define a symbol here where we call CMake -d for defining a custom symbol or parameter, and then give it the name of that symbol. In this case, IDF_target in all capital letters, and then we set the value of that, so equals ESP32S3. Then we specify the generator. As we saw earlier, ESP-IDF uses Ninja, so we're going to specify Ninja here. We'll give it the source directory of the current directory of Blinky, and we're going to specify the build directory, so -b, and specify the name of that directory that CMake will create. Once that's done, you should see the build directory with all of the extra files that we saw earlier when we're using the idf.py build meta tool. All of these files are generated because of this CMakeLists.txt. When we included the ESP-IDF CMake extensions, that's how ESP-IDF knows to generate all that extra stuff and specify the targets and everything else that goes into building a project for the ESP32. Now we're ready to actually build the application. So as we saw earlier, we can type CMake --build and specify the build directory. This will call Ninja to build our entire application, making sure everything is linked as needed. Once that's done, we should be ready to flash. So bring up a terminal on our host computer. Go into the directory of the repository where we've been working. You will need to activate the Python virtual environment if you have not already. Go into the Blinky directory, and we will call the python-m ESP tool to actually flash our application. Give it the port, say chip auto to let it auto detect which chip or variant it should be flashing to. Give it a baud rate, tell it to reset before and after, and then the actual write flash command. We will say dual I/O for the flash mode, set the flash frequency to 40 megahertz, set flash size to auto detect how big the flash memory is on our chip. Then we will specify address 0 for the bootloader. Note that this is for the S3 variant. Double check the address when you are actually flashing the bootloader for your particular variant. It might be hex 1000. Then we will specify the location of the partition table, in this case, hex 8000, and finally where it should flash the application binary at address hex 10000. Press enter, and it should flash. If you want to check serial operation, call python-m serial.tools.miniterm for that miniterm tool that comes with PySerial. Give it the serial port, in this case COM7 for me, and a baud rate of 115200. Sure enough, it should reset and give me the LED states on and off. You can press Control, close bracket to exit out of that serial terminal. Because we did not make any changes from our Getting Started with ESP-IDF video, the LED should be blinking just the same. While you can use ESP-IDF without interacting much with CMake, I find it very helpful to understand the fundamentals of the tool so you can do things like add components and customize your project. We'll see some of this when we make custom components in a future video.